So I'll be talking about some recent work with my collaborators, Nicolas and Ulysse. It's on the archive here if you want to take a look. Right, so some motivation for this project. Everyone here is a fan of phase-space methods, and phase-space methods have for a long time been used to define various notions of non-classicality. The most common and popular being Wigner negativity, but there are other notions, especially on the CV side, CV meaning continuous variables, such as Glauber-Schuderson negativity, or the more recent stellar rank, and there's a few others. Also, of course, in the DV world, there's lots of different measures of non-classicality based on phase-space techniques. Wigner negativity is quite successful, both in the original, harmonic oscillator continuous variable sense, and in the odd DV sense, the odd finite dimensional sense, as a few presentations have summarized. And it's been successfully applied to the magic state model of quantum computation. And this success kind of comes in two forms, a carrot and a stick. The carrot is that the negativity in both of these scenarios has very strong ties with quantum contextuality and magic monotones. On the other hand, the stick is that positivity is easy to simulate via Hudson-like theorems and Gottesman Kitaev type theorems. And so together with these two general ideas, this has led to a common idiom that Wigner negativity is generally interpreted as a necessary resource for quantum advantage. Sufficiency is a bit of a different question, especially as Michael's pointed out, but yes, certainly necessary at the least. So the problem, I didn't stagger these slides. So the past few years, we've seen a growing mismatch between the Wigner negativity of the original Wigner function, the continuous variable Wigner function, and resourcefulness in the GKP code. GKP code, which I'll summarize later, is a very important bosonic code. And this mismatch has kind of come in two different forms. The first is that encoded Clifford circuits are efficiently simulable despite having arbitrarily high Wigner negativity. So you have a logical Wigner function that lives on an abstract d-dimensional space. You can compute the dv Wigner function of a stabilizer state, say. It'll be positive. You encode into a CV harmonic oscillator. You compute the harmonic oscillator Wigner function for the code words, and you have all this negativity. So of course, this is to be expected because these are very often code words are very strange states on the physical level. But still, from a phase-space perspective, we would like to still have this idea that positivity is classical and negativity is quantum. And so we'd like to kind of fix this false negativity that's arising when in the presence of a quantum code. Right, so I mentioned that we have encoded Clifford circuits are efficiently simulable, but on the other hand, when you add to these circuits the vacuum, which is considered to be the least resourceful state from a continuous variable perspective, when you add the vacuum to this setting, suddenly you have universal quantum computation in the presence of the GKP code, at least. And so it seems like the role of negativity has swapped. We have got a Wigner negative circuit that's easy to simulate. You add a Wigner positive element, and suddenly you have universal computing. And so that's a bit of a strange state of affairs, especially if you're a phase-space theorist. We'd like to solve this. And so from a resource theory perspective, you can see this as saying, when we are in the Gaussian resource theory, or the resource theory of non-Gaussianity, if we restrict from all Gaussian operations to just encoded Cliffords, the set of resource states change. But we're still using the same Wigner function. And so the notion of Wigner negativity is being challenged in this context. And so it suggests that the original CV Wigner function, and more generally the physical space Wigner function, is not the appropriate object to use. And you can see further that this problem is quite generic. It's not just for the GKP code. It's for any encoding. Surely, most of the time, the code words are going to be Wigner negative from when you compute them through the physical space Wigner function. And so we try to tackle this problem, and we do this by taking a look at the physical Wigner function, in the case of the GKP code, the harmonic oscillator Wigner function, and we quotient this Wigner function by the stabilizer group. The idea is that the original Wigner function isn't sensitive to the symmetries that define the code space. So the solution is to quotient this Wigner function to obtain a new object on a reduced phase space that is aware of this, the symmetry that the code space defines. Okay, so that's the overall idea. And so now we'll just kind of go through these things a bit more slowly. I got my thing. thing here. So just a brief review of phase space and Wigner functions. It seems many of us here are more on the discrete variable side, but I'll just kind of put these two in parallel to show you how similar they are. The phase space in the continuous variable side is the plane, R2. And on the discrete variable side, it's the d by d grid, or the toroidal lattice, because there's a periodicity here. We have got the continuous axes, which is position and momentum. And here we have discrete axes, which is the computational basis and the Hadamard basis. Gaussian operations, or Gaussian unitaries rather, are certain area-preserving maps of this R2, whereas here we have Cliffords, and they are certain permutations of the d by d grid. So kind of like area-preserving maps, but in a discrete sense. And the Wigner function. So the CV Wigner function is going to be the set of expectation values for the parity operator basis. So for every point on the plane, we get a parity operator, a particular sum operator. The collective expectation values of all these operators forms the Wigner function, and they happen to be parity operators. And this is defined by acting on a position state, for example, and mapping to the -1 here. Exact same thing happens in the odd-dimensional dV side. We've got a collection of phase point operators. They all happen to be parity operators, which are defined analogously here. Another way to express the parity operator, at least at the origin, is the uniform sum of all of the displacement operators. Perhaps less, but you can also see this as a certain evaluation of the symplectic Fourier transform of the parity operator basis. But the key thing is that the one at the origin is the uniform sum of the displacements. Same thing in the dV side. We have the analogous Weyl displacement operator. These are the clock and shift matrices. This is the modular inverse of 2 in the field ZD, or the ring ZD. And we end up with the parity operator at the origin. Okay, so that's phase space and Wigner functions. But now I want to present a bit of a more abstract way of building Wigner functions, a more general framework, which I'm calling symmetry-based phase space quantum mechanics. And this comes from a very important paper by Briff and Mann from 1999. And it says phase space formulation of quantum mechanics and quantum state reconstruction for physical systems with Lie group symmetries. So it's defining a whole family of Wigner functions based on an initial choice of Lie group. And so we start with a symmetry group G. It acts irreducibly on some Hilbert space. On that Hilbert space, we pick some fiducial state. And I'll give an example of this right after. We have a fiducial state. Through the irrep, we find the subgroup of G that fixes your fiducial state up to phase, and only generates a phase. We then quotient the original group that you started with by this isotropy group, and this creates the phase space manifold. This is how you can obtain a general phase space manifold. You can think of the choice of fiducial as choosing the origin of that phase space. Now that you have the phase space manifold, you then propose a collection of phase point operators, so an operator-valued map on this manifold, and then you demand that these phase point operators satisfy a whole bunch of conditions. And these conditions are sometimes called the Stoyanovich axioms, which you may be familiar with. I won't go into the details, but these are very natural axioms that often are uniquely, or not uniquely, but they often characterize a Wigner function to a high degree of precision. Once you have these, and that's where the hard work is demanding and ensuring Stoyanovich satisfaction. Once you have these, then the Wigner function, the generalized Wigner function, is going to be the expectation value of all of these operators, just like we had before. Okay, so that was a little abstract. Let's do a quick example for the original CV Wigner function. The ambient group is the Heisenberg-Weyl group. It's the 3x3 matrices with 1s on the diagonal and real numbers in the top right corners, with an appropriate group law. The fiducial state is going to be the vacuum. The isotropy subgroup will be U1. This is, of course, because Heisenberg group is generated by the identity matrix, position operator, momentum operator. So e to the I theta identity is only going to generate the phase. And so then we do this quotient. We end up with Heisenberg group quotient U1, and we get R2. And this is how you can obtain the classical phase space R2, but from a kind of more quantum mechanical, like from the Heisenberg group, you can get the classical phase space. You then do the work, and you ensure that these Stoyanovich axioms are satisfied, and then you can derive that the that the phase point operators must be the parity operators. So this is the one at the origin, as I just mentioned, and now here all the other ones are just going to be the displaced versions thereof. Okay, so now we applied this. We came up with a general framework that basically just piggybacking off of the work of Briff and Mann, but we do a key generalization. And I won't go into the more general framework, but I'll give the example of its application to the GKP code. But just in case, I need to just briefly discuss what the GKP code is. So as I mentioned, it's a very important quantum error correcting code. It takes a qudit, so a d-dimensional system, and encodes it into a d-dimensional subspace of a single bosonic mode. So a harmonic oscillator. It's a stabilizer code, and so it's generated by stabilizer generators. And these two generators are given by two displacements. One is the shift vertically by an amount root 2 pi d. This is units where h bar equals 1. And the other one is shifts along position by the same amount, root 2 pi d. This is an abelian group, and it's going to be isomorphic to essentially z cross z. And so you can think of this subspace, this d-dimensional subspace, as the collection of continuous variable states that are 2 pi d, root 2 pi d periodic in both position shifts and momentum shifts. And this implies that if you were to compute the harmonic oscillator, the CV Wigner function of any of these code words, it's also going to have to be periodic with the same periodicity. So that's the GKP code space. And importantly, both stabilizer states and magic states are highly Wigner negative. This is the initial problem that I mentioned earlier. So that's the GKP code. The most important thing is just the stabilizer group. And now, okay, well, I'll just, a little bit more intuition. For example, the code words of the computational basis are going to be what are called Dirac combs. These are just combs of Dirac delta functions that have been separated by an amount root 2 pi d. So this is the encoded 0 computational basis state. This would be the encoded 1 computational basis state. It's exactly the same, but now it's been shifted by a little amount here, and this shift is going to be 1/10 the distance of the stabilizer shift. So now we know what and of course that we have d total of these computational basis states, labeling 0 to d minus 1. Okay, so now the key thing that we do is that we take this Briff and Mann kind of procedure of building phase spaces using this choosing a group and fiducial and so on. But the key thing that we change is that instead of picking a fiducial vector, we pick a fiducial space. And that fiducial space will be the GKP code space. So we're asking for all of the group elements via the Heisenberg-Weil group that keep every single state inside the GKP code space the same up to phase. And so this is, of course, by construction, just going to be the stabilizer group. We still have the same U1 because, of course, e to the I theta identity is also going to generate phases. We do the quotient. You can kind of think of doing the U1 first to get R2, and then now you quotient R2 by Z, and you get a continuous torus. And so now this continuous torus will be the phase space that is of interest for this work. Now you do the hard work of trying to ensure the Satonovich axioms on the phase point operators, and you find that the phase point operator at the origin looks like this. So this is why I brought up this way of looking at the phase point operator at the origin, because you can see here it's kind of similar. We have this funny phase factor out front, but it's similar in spirit, these two. All the other phase point operators on the torus is going to be displaced versions of the undisplaced one. So now this object we're going to call the Zak-Gross Wigner function. And it's an unfortunate circumstance that David's not here to see this. I'm equal parts disappointed and relieved that I don't need to do this. But yes, so we called it this for I think, good reason. And so now we're going to just talk about why it's called this. And basically, I'm just going to tell you about the properties of this Wigner function and argue why it solves the initial problems that we talked about before. So the phase space, as I mentioned, we've got this continuous torus, also called the stabilizer cell in GKP literature. We've restricted to odd dimensions here. So why gross? So one thing that we showed, and kind of related to what you were asking earlier that it turns out, and this is a conclusion, this isn't this followed from enforcing Shatonovich, that the phase point operator at the origin of the torus you can actually think of as the encoded parity operator. And when I say encoded parity operator, I mean this expression here, where we have the encoded versions of the computational basis states. This bar means encoded, and it's taking you to J and mapping you to minus J. So this shows that this is a direct link between the dV theory and the CV theory through this equation here. And furthermore, if you were to apply a continuous variable displacement to this operator, but if you displace by a logical distance, which is again 1/10th the size of a stabilizer length, this new phase point operator is going to be the displaced gross parity operator. So this is saying that we have within the continuous torus, we actually have a grid along the logical sites that are associated to the same code space. And so this is the key thing that I want to mention, is that the Zak-Gross Wigner function can actually be seen as a continuous family of dV gross Wigner functions, one for every displaced GKP code space. And I'll have a diagram in a second that might help. And furthermore, if I take some native CV state, I project it to all of these different GKP code spaces, I'm going to end up with a bunch of dV Wigner functions. I put them all on the same torus, and then I get the Zak-Gross Wigner function. So let me just explain this again. That was a little abstract, so I've got a diagram that might help. So if we got the original phase space plane, this is R2, with position momentum. We have these two stabilizer lengths, like this, root 2 pi d. The displacement operators, these are the generators of the stabilizer group. They commute as they must because the stabilizer group is abelian. This means that if we can measure these two at the same time, when you measure a displacement operator, what you get in return is an eigenangle. An eigenangle, though, is only unique up to 2 pi divided by the shift amount. Okay, this also happens to be the same thing as the logical displacement. But this square of what you'll get can be seen as being this little logical cell sitting within the stabilizer cell. If you do this measurement, you get a pair of eigenangles, but the corresponding eigenstructure is an eigenspace. And that eigenspace is going to be the different GKP code spaces. So you can think of using this simultaneous diagonalization as decomposing the Hilbert space, the full infinite dimensional Hilbert space, as a direct integral over a bunch of d-dimensional subspaces. And these d-dimensional subspaces are parameterized by these values in this orange square here. Like as I said before, you can actually identify these displaced, these code spaces, these subspaces as the displaced GKP code spaces. And for those who know, this is actually exactly just what the syndrome distribution lives over. But we also know that in the case of the undisplaced GKP code space, eigenstates are going to be 2 pi d periodic, and therefore they only have support on a lattice, this lattice, and they're periodic, and so we can restrict attention to this stabilizer cell. And so this is now we've arrived again at the stabilizer cell torus, the continuous torus that we derived earlier. If we look at this sublattice of the torus, we get the dV phase space associated to the GKP code space. And if I were to shift this lattice a little bit, say to this blue lattice, I get a new dV phase space, and that's now associated to a different GKP subspace. It's going to be it's also called an error space. So these are the displaced, I've been saying displaced GKP code spaces. I just mean that we have a bunch of lattices that together form the continuous torus. And each of these lattices are associated to different code spaces. And so again, I'll say the same thing again. The Zak-Gross Wigner function is the collection of dV Wigner functions, one for every displaced code space. So it's a really hybrid object. It's both a continuous function, but you can also think about it as consisting of a continuous family of discrete objects. Okay, so that was answering why gross. So now why Zak? I won't focus too much on the Zak part, but so now that we have this collection of dV Wigner functions, we can perform the collective marginalizations. So if I have, for example, d equals 3, if I if I were to stick to the top lattice, like the undisplaced code, I would just take that point, add it to that point, and add it to that point, and I would get the point there. I do that for all the different GKP, for all the different dv Wigner functions. I get a two-dimensional distribution as a marginal, which is the collection of all the dv marginals. This area happens to be 2 pi exactly, the d's cancel. And you can think of this as what's called a Zak measurement distribution, which has very deep connections to modular variable theory, which you can sort of think of as what happens if you simultaneously measure now a stabilizer together with a logical. Before we were measuring two stabilizers, now we're measuring a stabilizer and a logical. And then the resulting eigenangle that you get was going to be on a patch of area 2 pi. This is called a Zak patch. So it's a very nice connection to the whole world of modular variables and Zak theory. Now the same thing happens, of course, if I were to do the other shift, if I were to go horizontally instead of vertically. And so this introduces the idea of conjugate Zak patches. And this is nice because it gives us some intuition on how to interpret Zak-Gross negativity. It's the inability to build a joint distribution given conjugate marginals. This is exactly analogous to the continuous variable case, where you have a bunch of homodyne data, a bunch of quadrature distributions. You try and reconstruct a joint distribution based on the quadrature data. Negativity reflects the inability to do so. And same thing happens on in the dv case. And that's the core concept in the proofs that connect Wigner negativity to contextuality with respect to the Pauli measurements / homodyne measurements. Okay, high time for an example. Oh, and I should just mention, before even getting to the example, the fact the previous slide I had of interpreting the Zak-Gross as a collection of dv Wigner functions, this actually already solves the first problem that I mentioned. And this goes to the question that you asked. If I were to compute the Zak-Gross Wigner function of a stabilizer state, of an encoded stabilizer state, I would just get what the Gross Wigner function is on the appropriate lattice. And so stabilizer states would remain positive in this picture. So problem 1 has been solved. Now the second problem was, just to remind you, was when when we added the vacuum. Suddenly it became the circuits became universal, and so now we compute the Zak-Gross Wigner function for the vacuum. You do the calculation, which I'm not going to detail. You get this infinite sum like this, and this is what it looks like. This is the Zak-Gross Wigner function for the vacuum, which happens to be for the GKP code with dimension d equals 13. It has to be odd, of course. This formula here happens to have the exact correct form to be what's called a theta function. And so this also naturally connects to the other universe of theta functions, which the GKP literature is slowly encroaching upon. So this is contributing toward the merging of these two fields. I won't go into details, but it's a nice mathematical connection. But of course, the key thing is that it takes negative values. And so now the vacuum is Zak-Gross negative, which is returning the intuition that we originally wanted of negative things being resourceful, positive things being resourceless. Coherent states, of course, are just going to be translations of the vacuum. These are going to be just translations of this whole object, but with periodicity 2 pi d. Another example is the thermal state. So of course, the thermal state is the thermal state with respect to the harmonic oscillator Hamiltonian. You can again compute the Zak-Gross Wigner function. It's quite similar to the vacuum. It's also can be written as a theta function, and it looks like this. So now I just want to mention briefly, I've slightly displaced this. So on the other slide, we had a lot more of the positive and negative regions, but the periodicity, I think, can sometimes mislead the relative size of the structure. So I've just displaced them so that you don't get trapped by the periodicity of the space. So we got four kind of regions, 3 positive, 1 negative. You can also write this as a theta function. And what's interesting about this one is that, okay, well, and of course it reduces to the vacuum for 0 temperature, as it must. But what's interesting about the thermal states is that as you increase the temperature of the thermal state, these positive regions increase and this negative region decreases until finally the negative region actually disappears at a critical temperature, which means, well, that has a few implications. So what does that mean? So we're looking a little bit at the numerics, and going back to this figure here, it seems like the most negative point is at the very center, of this negative region. And so we, as a kind of preliminary test, we can use this as a witness for Zak-Gross negativity. If this thing is positive, then the whole thing is positive. So with that being the assumption, which is almost certainly true, but still an assumption, we can use that, we use that as a witness. And it seems that this is, you can view this inequality as a sort of classicality inequality. So if you violate this inequality, then you have Zak-Gross negativity in your thermal state. N is the number operator, D is the dimension, and V is what's called the covariance matrix of the original Wigner function. And this is just a brief aside that as a nice geometric intuition is that you can think of the determinant of you can think of the left-hand side here as essentially telling you how big the thermal state is as it sits on the full R2 plane. And we already know that the area of the stabilizer cell is 2 pi d. So up to some scaling factor, you can actually you can conclude that a thermal state is Zak-Gross Wigner negative if the CV Wigner function is basically small enough. If it sits within the stabilizer cell, then it's going to be Zak-Gross negative. So that's just as an aside, that's a nice geometric intuition. Another consequence of this is that the resourcefulness of a fixed CV state depends on the dimension of the GKP code. You can have the same thermal state that's resourceless for D equals 3 GKP, but resourceful perhaps for D equals 13 or something like that. And for any dimension D, there's a critical temperature where the thermal state becomes positive. And this is what that plot looks like. So on the x-axis, we have temperature, and on the y-axis, we have the value at the very center of the negative region. So as you can see, for any given temperature, you go up, you can see that certain curves are above 0 and certain curves are below 0. We included D equals 2 just for interest. We originally started by only assuming odd dimension, but of course, once you get theta functions involved, they don't know about dimension anymore. It's just a formula. And so out of interest, we just included this. And it's interesting that it happens to fit. It doesn't seem to stand out in any particular way. Okay, so that's thermal states. And now I just want to maybe say a word or two about another way of interpreting the Wigner negativity of the Zak-Gross. We already mentioned that it's sort of can be seen as an obstruction to building a joint distribution over conjugate marginals, but we can also relate this to the negativity of all the dV Wigner functions. So as I mentioned, we have a bunch of code spaces. We've got a CV state. We project them to all these different code spaces. But when you project a state to a code space, it's going to be subnormalized because it's not a unitary transformation. And that subnormalization actually has an interpretation, like how far it is from being unit, which is the probability of collapsing to that code space when doing the syndrome measurement. So all these dV Wigner functions that come up with that together create the Zak-Gross Wigner function, they're all not normalized. But the difference that they're not normalized by a probability, and that probability is the collapse probability. So this means that if you were to compute just the L1 norm of the Zak-Gross Wigner function, you can reinterpret that as just the weighted average of all of the dV negativities, weighted by the probability of collapsing to that particular code space. So that's another way to interpret the Zak-Gross negativity. And finally, if you do a double marginalization, we collectively marginalize one direction, and then we further marginalize again, we get an even smaller square. This square happens to be exactly the syndrome distribution. And here's a nice schematic that summarizes what I just said. So we've got the full Zak-Gross phase space. We marginalize one way, we get the vertical Zak patch. We go down, we get the horizontal Zak patch. And if we were to marginalize again in either direction, we get the syndrome distribution. Okay, so those are the properties of the Zak-Gross, and that's the majority of what we wanted to talk about today. I have one final example, is the physical GKP state. The ideal GKP states are, of course, there are these infinite Dirac combs, and so they're highly non-normalizable. In fact, strictly speaking, they're not actually in Hilbert space. They're in what's called the rigged Hilbert space. That's not a critically important thing from a mathematical perspective, but in the lab, of course, you can't build these things, and so you need to create what are called physical GKP states. Now, physical GKP states, you can think of, instead of a collection of Dirac delta functions, you have very thin Gaussians that are approximating Dirac deltas, and then you have an overall Gaussian envelope. So these are the very thin Gaussians, and this is the Gaussian envelope. And J is which computational basis you're in. which computational state you're in within the computational basis, and these k and sigmas are just parametrizing the Gaussians. This is what the full Zak-Gross situation looks like. It's interesting. This is for d equals 3, and this is for certain values of the damping parameters. Again, slightly shifted just so that we don't get confused by the periodicity structure. And you can see that it's actually a bit slightly negative, which is quite interesting. That physical GKP states are actually technically resourceful, or they appear to be resourceful. And as you let these approximate GKP states become ideal GKP states, you let the Gaussians get thinner, the envelope become weaker, and it becomes the ideal Dirac comb. These three positive blobs, they get thinner and thinner. These weak regions here, they get smaller and smaller until finally you end up with just 3 delta functions, which is exactly the dV Wigner function for a stabilizer state. And these are the 2 Zak marginals, and this is the syndrome distribution. And again, of course, in the limit of perfectly ideal, this would become a point. Okay, so that was what I want to talk about today. So the summary. So there's been a sort of recent mismatch. And mismatch maybe isn't the right word, but a kind of conceptual bump that wants to be resolved between Wigner negativity and resourcefulness in the GKP code. It's actually a very general phenomenon that can occur in principle in any stabilizer code. And we address this by basically quotienting the physical space Wigner function by the symmetry group that defines the code, the stabilizer group. In the case of GKP code and in the case of odd dimensions, the resulting Wigner function that results is what we call the Zak-Gross Wigner function. It's named this way because it has strong connections to both of these names. Just to reiterate, it's a continuous family of dV Wigner functions, one for each of the displaced code space. It's a joint quasi-probability distribution with respect to conjugate Zak marginals. So that's the Zak and that's the Gross. And the negativity volume you can think of as the expected dV negativity volume weighted by the syndrome extraction probability. This resolves the problem. We have got stabilizer code words are positive, magic code words are negative, vacuum is negative, and low temperature thermal is negative, which is in agreement with the if you're familiar with this all Gaussian universality paper from Xanadu from 2019. And the negativity of the fixed GKP state depends on logical dimension. This sort of makes sense. We have this kind of picture that the stabilizer cell defines a characteristic size on the planar phase space, and then depending on the size of the CV Wigner function is relative to the stabilizer cell, that can kind of give insight onto the when the Zak-Gross will be negative, and that the physical GKP state is very slightly Zak-Gross negative, which also agrees with other simulation results. Okay, so that was the summary. So the outlook, so some future work, a few of which that we're trying to work on. So this kind of contributes to the question of sufficiency of Wigner negativity. So the idea is perhaps in the presence of a quantum code, if you do this appropriate quotienting, maybe it's actually the negativity of this reduced object that is both necessary and sufficient for a quantum advantage. That's, of course, a big statement that may or may not be true, especially in light of the lambda polytope. So we'll see how that stands. Of course, this can be applied to other codes. It works best, or not best, it works rather well for the GKP code where the ambient space is just one harmonic oscillator. But in principle, this argument applies for other quantum codes, including ones that are just dV to dV, and perhaps into code concatenation as well. In the specific case of GKP, one thing could be done was we develop a sort of a simulation algorithm, a Gottesman Kitaev type theorem based on certain Gaussian transformations. We want to look at the even dimensional case rather than the odd dimensional case, because now I'll just briefly say that the framework that we came up with of producing a reduced phase space, generating a Stoyanovich satisfying set, that doesn't know about the even odd distinction at all. That's just a framework. We stuck with odd dimensions because we realized later that the odd ones happen to reproduce the Gross parity operator, but in principle it works for even. Perhaps this will be a collection of Wüter's Wigner functions rather than a collection of Gross Wigner functions. This is ongoing work. Another thing to do is to rigorously obtain these thermal state inequalities. The plots I showed you were just numeric. I think they're probably correct, but it'd be nice to show them properly. This involves manipulating theta functions and knowing about theta functions. The first one's actually already been done by a recent paper a few months ago by Cameron Kalkuth and collaborators. You can take a look at that if you're interested. They do a simulation algorithm based on a positive Zak-Gross function, encoded Cliffords, and I think a few more. They do also symplectic transformations with integer coefficients. But yeah, check this paper out. And more foundational, it'd be interesting to connect to the theory of marginal of Leggett-Garg inequalities, which has come up in the context of modular variables, and this actually been done in the lab too recently. And finally, it'd be nice to connect Zak-Gross negativity to contextuality, just like that's been done for the other Wigner functions. This is also some ongoing work, but the idea would be that the set of measurements that produce contextual data would be the modular homodyne measurements and the conjugate Zak patches. So yeah, so that's the outlook for future work, and yeah, thank you very much.